Yes, students, are you able to see the PPT?
Yes, sir.
Okay.
Yes, sir.
So I will today revise the common emitter short circuit current gain and with some additional parameters and one question numerical I will discuss with you. Here already we discussed, it is just a revision for common emitter short circuit current gain. See, hybrid pi model. Already we know this hybrid pi model. It is for common emitter transistor. RBB dash is base spreading resistor. It is here. It can also be represented as GBB dash. That is conductance. This is equal to 1 by RBB dash. Now this terminal is B dash terminal. It is at the internal of the transistor. Already you know this, right? This circuit diagram. Here base is the external terminal and B dash is the internal virtual terminal. Between B dash and this point there is a resistance will exist. Internally it is RBB dash. Between B dash to E terminal, internally there is a resistance REB dash. And between B dash to C there is a internally one resistance will be formed, that is RCB dash. And we know that there is the capacitance at the junction of base and emitter here, and a capacitance will be formed at the junction base and collector. So that thing is modeled here. RB dash E, it is the resistance between B dash and emitter terminal. So from B dash and emitter, I have drawn this resistor. It can be represented as in terms of conductance GB dash E. This is equal to 1 by RB dash E. Right? We know that conductance is the reciprocal of resistance. Now between B dash and E terminal, as I said, internally one capacitor will be formed, and that is your CE. Now between B dash and C, see in this diagram, between B dash and C, you find one resistance RCV dash and one capacitance will be formed between the junction. So that is represented, this is B dash and this is C terminal. Between these two we have one resistance R B dash C. This is feedback resistance and an internal capacitance CC. Now, so now at the output side you see this is collector, this is emitter. Across collector and emitter you will find this voltage VCE. You can find this voltage VCE. Then there is a resistance between collector and emitter RCE, and conductance. In terms of conductance you can represent this resistance as GCE is called dependent current source, represented by GM, that is a conductance of the transistor, multiplied by VB dash E. VB dash E you find here at the input side. This VB dash E is here, right? So this current source is depends upon the input voltage VB dash E, right? Okay. Now we will find, so this is important question from the examination point of view also, common emitter short circuit current gain. For this we will use hybrid pi model, right? Hybrid pi model. So this is figure 1, which is your hybrid. Now you see here RCB dash, RB dash C and CC. These two capacitance and resistances, they are acting as a feedback element, right? Because both of them are connected to C, which is your output terminal, and they are connected to B dash, which is your input terminal, right? So they are acting as a feedback element. So for the simplification of the circuit, what we will do, we shall use the Miller's theorem for the simplified circuit, right? Now see here, this is, if this type of circuit you will find where a impedance Z is connected between input point A and output point B. So here Z is also a feedback element. Then we can split this Z into Z1, which is connected to input side, and Z2, which is connected to output side, right? In this way. So this Z can be removed, and in place of Z, you can connect Z1 at the input side. This is your input side, and you can connect Z2 at your output side. The values of the Z1 is Z divided by 1 minus voltage gain. So this will be the case when this Z is resistive, when it is a resistance. But if Z is a capacitor, then here in place of this Z1 we can connect one capacitor C1, and its value will be C multiplied by 1 minus AB. Same way for the output side Z2. If this Z2 is a resistance, then the value of this Z2 will be Z. Z is this your overall in your original circuit, whatever is the value of Z. Z by 1 minus AB inverse, that is 1 minus voltage gain inverse. And if Z is capacitor, then in place of Z2 you can mention C2. So this can be represented, the value of this will be C multiplied by 1 minus AV inverse, right? So with this concept, what we will do, we will split this feedback resistance and feedback capacitance, and we will bring them towards the input side and towards the output side. And this will be done for the simplification of the circuitry. So now you see, we will get this diagram. If you recall this diagram, only thing is at the input side, we have added one Z1 which represents this, and C1 which represents RBB dash, it was there, RB dash E, it was there, CE, it was there. These three things were already there. The feedback resistance is splitted here and it is connected here. Now what is its value? RB dash C divided by 1 minus AB. See here. If your Z is AB, voltage gain. And we have one capacitance also as a feedback capacitance. So its value will be this. Value of the capacitance multiplied by 1 minus AB. So see here, I have connected one capacitance also. That is your CC, feedback capacitance, multiplied by 1 minus AB. Only these two additions is there in this input side. Now at the output side, we have to connect this Z2, which will represent the feedback resistance. So this is represented by here. You see this. What is the feedback resistance? RB dash C. See here. What is the feedback resistance? This RB dash C. Right. So here we have connected this resistance and its value will be with this formula. You write RB dash C divided by 1 minus 1 by AB. 1 by AB. This is 1 by voltage gain. This is your AB inverse. In formula I have written this AB inverse. So this can be written as 1 minus AB also. So and the feedback capacitance, its value will be C multiplied by 1 minus, yes. Yes, any question?
So you have not covered the cascade amplifier.
A cascade amplifier is there. But it is too many topics are there, right? So if you will go with all the topic, then I don't know whether how much you can do. So that's why I am revising these things also, so that it will be easy for you to remember. Cascade is simple. It is simple. I will send you the notes, right? Or in between, if we find time, then I will take one additional class and I will cover that, right? From Monday, you are having fourth semester classes now. But additionally, in between, I will find the time and right on some Saturday or on Sunday, I will take one class and cover that. Okay, I am revising these so that it will look easy for you, right? Only cascade is there. That's all. And because see in unit 4, it is from unit 3 and 4 both. Huge number of derivations are there. So I doubt how much you can remember. That is the thing. And its value is CC 1 minus AB inverse, right? And remaining thing is same, RCE and RL. It was already there. So this figure is after Miller theorem on feedback component. Okay, so same figure I have repeated here. Now short circuit gain we have to find. So if right, then the voltage across RL. And what is the voltage gain? Voltage gain is output voltage by input voltage, that is VCE divided by VB dash E here. Yeah, okay, already I have written here. No, this is VBE, and here you have to find VB dash E, because VB dash E is different from VBE. This is the voltage gain. Now, if due to the short circuit VC is 0, then this is 0 divided by this, so voltage gain will become 0. So due to short circuit, all the component connected in parallel to the short circuit will also become short circuit. So in output side, in output circuit, RCE will be short circuited, this will be short circuited. This capacitor, it will also be short circuited. Then this resistance, it will also be short circuited. So all of these three are short circuited. But here this current source, it is depending upon the input side voltage. So it will not short circuit, right? It will not short circuit. In the input side, this resistance, since AB is 0, so this can be written as RB dash C, because AB is 0. And this capacitance, since AB is 0, so this also can be written as CC, right? So now we will get new figure. This is the figure now. So here already this is the same resistance, this is the same resistance, this is the same capacitor between B dash and E, and now this is the RB dash C, and this is the CC, because your voltage gain has become 0, right? So in place of this resistance, you will get only RB dash C, and in place of this capacitance, the value will be CC, right? So that's why it is here RB dash C and CC. Okay. Now, if we are seeing the equivalent resistance from a point, then ignore capacitance. Means from here, if we are looking inside, so there are capacitances and resistances are there. So when we are looking for resistance, then ignore capacitances, these capacitances, ignore that. So we will get the Rin. Rin will be RB dash E in parallel with RB dash C. RB dash E in parallel with RB dash C. Now, see, already we know that if there is a NPN, any transistor is there, suppose this is emitter, base, collector. Or I will, or you come to this point here in this diagram. Yes. See this resistance and this resistance. This is at the emitter side. Since the doping in the emitter is more, so this resistance is less. Its value will be less. And doping in collector is less. So this resistance is more. Right? So RV dash E is having a small value and RCB dash is having a higher value. So at room temperature, RB dash is 1K and RB dash C is 4000 K, means 4 mega ohm at high frequency range. So you can, if RB dash E is very small, RB dash C is very big, then these are the in parallel combination, then its equivalent value will be nearer to the 1K. right? So you can ignore RB dash C. This RB dash C can be ignored. So we will get this figure now, right? RB dash C I have ignored here, and this is the figure now. Now in output side, since due to a short circuit you are having this short circuit current, so ISC is equal to minus GMVBE, this current. IC is equal to minus GMVBE. Only there is a difference in the difference in the direction. Otherwise, remaining thing is same. That's why minus sign is kept here. Now in the input side, you see the input side. This is VBE. IB current is flowing. This is RB dash B, and here we have connected Z in, right? So this combination is replaced by Z in here. So Z in will be, so now here you have this resistance. It is in parallel with these two parallel resistances, capacitances. So the overall value of Z in will be RB dash E multiplied with 1 by J omega CE CC, right? Because CE and CC, they are in parallel, and since they are capacitance, so equivalent capacitance will be CE plus CC. Divide by RB dash E plus 1 by J omega CE by CC. Okay. So this is Z in. So now if many things are in parallel, then impedance become complex. So in place of impedance, we write admittance, right? So Z in terms of admittance, it is 1 by Z in. And this will be, you simply write this expression as 1 by Z in. So you will get one term as 1 by RBE dash, and second term is 1 by J omega CE CC. You can do this by yourself. And 1 by Z in is your admittance. 1 by RB dash E. In terms of conductance, it is GB dash E. And this term is written as J omega CE plus CC. Right? This is RB dash, RBB dash, this is admittance. And across this admittance, you are having a voltage VB dash E. This current is flowing, IB is flowing through YN. So VB dash E is IB multiplied by ZN, right? This voltage is the voltage across this admittance. And VB dash E in terms of admittance will be IB multiplied by 1 by YN. Now we multiplied both sides by GM. So we will get GM VBE here. GM multiplied by VBE and GM multiplied by IB by YN. But already we know that short circuit current, see here, this side, this. Okay, you are getting the voice? Student, someone respond. Are you getting the voice?
Yes, sir.
Okay, okay. Because I was disconnected here due to internet problem. Okay. So I short circuit is this. Or you can write it as minus I SC E. So here I have written this, right? And GM V dash E is this. Already we have done this, right? So you can get ISC. ISC is equal to GM IB Y YE. This. And this IB I will bring towards the left side. So I will get, and minus sign I will shift toward the right side. So I will get I short circuit divided by IB is equal to minus GM by YN. And this is only the current short circuit current gain. This is the short circuit current gain. And it is equal to minus GM by YN. So, okay, up to here we have done. Now Yin value from here. I will put this value in that expression. So short circuit current gain is minus GM divided by GB dash E. This expression is the expression of Yin. Now numerator and denominator I will divide by GB dash E here. So GM divided by GB dash E, and in denominator also if I divide, then I will get this 1 plus this term, right? Or this is equal to here. Now the values of typical value of GM is 50 milliampere per volt and GB dash E is 1 milliampere per volt. So the ratio GM by GB dash E is, and 50 HFE is also 50, right? We know the typical value of HFE. So the current gain in the numerator we are having this. So this value is, typical value is 50, and this can be represented as HFE. So we are having this minus HFE divided by this. So this will be the expression of your short circuit current gain. If question is asked up to the finding the expression of short circuit current gain, you can calculate up to here. But apart from this, you can calculate up to here, or you can calculate, or it is better to calculate it up to here. Up to here. So see here, this RB dash E. RB dash E, already we have this R in. This R in is RB dash E parallel to RB dash C. But since R B dash is very small, so R in will be your R B dash E, right? So same thing I have written there in terms of R B dash E. R B dash E I have written as R in, right? So here this is R in and this CI. CI is the equivalent capacitance. Two capacitances are there in parallel, CE and CC. So that sum is written as CI or C in, right? So now this expression I will again further write it as 1 plus j in place of this omega. I will write 2 pi f and R in by C I will brought it in the denominator part like this, and this will be written as this minus HFE 1 plus j. This is j and 2 pi. Further I will bring 2 pi at the denominator. So 2 pi is here, only f part is there, right? And this term is represented by f beta, right? So f beta is this. So final expression for short circuit current gain, you can remember this also, minus HFE divided by 1 plus j f divided by f beta, right? Where f is the operating frequency at which your circuit is operating, and f beta is called as common emitter short circuit current gain cutoff frequency, right? And the value of f beta you can find out by this expression or this expression, right? Now the magnitude of current gain, right? Magnitude, see here the current gain, this expression is there. In the denominator there is j term. So if you find the magnitude, then magnitude you write in this way, minus sign, I have removed the minus sign, HFE divided by whole root 1 plus f by f beta whole square, right? So this is f beta. So to find the magnitude of the current gain, short circuit current gain, you require HFE, you require frequency of the operation, you require f beta, right? And there is another term, FT. It is the frequency at which common emitter short circuit current gain become unity. The short circuit current gain when become unity, at what frequency this happens, that is your FT. So this current gain magnitude should become unity, and formula for the current gain is, magnitude of the current gain is HFE divided by 1 plus f by f beta whole square. Now this f, frequency at which the current gain will become unity, so that is the operating frequency now. So that is your FT. So this is the FT, right? Here I have written FT this. So, and always remember, value of this FT is greater than beta. So if this is the condition, T is greater than F beta. So this term is, you can neglect this one. So you can write it as equal to H Fe divided by F beta whole square. And if you now what we will do, we will do the square of the both sides. So I will get 1 is equal to H Fe square divided by Ft square square. Or this I can write it as Ft square by F beta square is equal to H Fe square. And from here we will find out the value and this will be H Fe multiplied by F beta. So this is the expression of Ft, right? So, and you can see here HFE is around 50 and 50 is multiplied by F beta. So the value of Ft will be 50 times greater than F beta. That's why Ft is greater than F beta. It is around 50 times higher than F beta. So what is your Ft? How you define Ft? Ft is the frequency at which the common emitter short circuit current gain. Now there is another term F alpha, right? It is the frequency at which the transistor short circuit current gain drops by 3 dB by root 2 times from its value at low frequency, right? And its expression is F alpha is equal to 1 plus beta F beta, right? F beta is your cutoff frequency. So now based on this, there is one numerical. Suppose a transistor is operating at collector current of 5 milliampere. So IC is given, collector current of 5 milliampere at room temperature and has HFE 100, HIE 600 ohm. If its common emitter short circuit current gain is 10 at 10 megahertz. So this is frequency of the operation. At 10 megahertz, the short circuit current gain is 10. Then calculate GM, RB dash E, RB dash, FT, F alpha, and CE. So here GM is transistor transconductance. If you go through this conductance which we discussed, this GM, transistor conductance GM, its value is IC by VT, where VT is thermal voltage and its value is 25 millivolt. Already I told you this. So simply you have to put the formula in this here. IC is given, VT is 26 millivolt. Therefore GM will be 0.192 ohm inverse, right? This is conductance. Now RB dash E. RB dash E, this term. So this is your, see, G B dash E. Already we have calculated this. What is this? This is input conductance R B dash E. See here. G B dash E, which can also be written as 1 by R B dash E. So this value we have already calculated. And this is G B dash E. This is reverse of R B dash E. So simply use this formula. R B dash E is equal to HFE by GM. So R B dash E is HFE by GM. HFE is 100. It is given in the numerical. GM already we have calculated here. So this value you put here. So you will get 520.83 ohm. Now RBB dash. See RBB dash. If you recall, this is B dash. This is B terminal. Now here internally there is a resistance. So this resistance is R base spreading resistance, RBB dash. So you remember this formula. See, basically HIE is input resistance, right? So if you see this figure, emitter, this is RB B dash, and here this is R B dash E, and here you have some input resistance HIE, right? So this HIE B dash E. From here you get the expression of RBB dash. So that expression I have used here. RBB dash is HIE minus RB dash E. HIE is given 600 ohm. RB dash E already we have calculated. So from here we will get this value 79.17 ohm. Now FT. So already we have seen this FT is HFE F beta, right? This value we have already calculated. This the frequency at which the current gain will become unity, that is FT. So it is a product of HFE. HFE is nothing, it is the current gain, that is beta multiplied by F beta, right? So in this formula HFE is given, but the value of F beta is not given in the numerical. So we have to calculate this. Calculation for F beta. Current gain is 10 for frequency 10 megahertz. This is given. Short circuit current gain is 10 for frequency 10 megahertz. Then the magnitude of the short circuit current gain is expressed by this. Magnitude of current gain, short circuit current gain is equal to HFE divided by square root 1 plus F by F beta whole square. This AI is given, put it 10, HFE is given, put it 100, Square root of 1 plus this frequency is given 10 megahertz divided by f beta. From here you solve this expression, then you will get f beta as 1.005 megahertz. So f beta is approximately it is 1 megahertz. Therefore ft is hfe multiplied by f beta. HFE is 100 multiplied by 1 megahertz. It is 100 megahertz. So see here ft is 100 megahertz, whereas f beta is 1 megahertz. So already I said you ft is greater than f beta always, right?
Sir,
Yes.
sir, next class started, sir.
Okay, this is just 1 minute. And f alpha.
Okay.
100. Beta is HFE into 1 megahertz. You will get 101 megahertz here. And in the last CE, right? For CE, you use this formula GM divided by 2 pi F. Just now we have calculated 100 megahertz. With this, you will get the value of this CE, right? So CE value is around 307 picofarad. Okay, so sometimes I will take one class extra additional. Okay, so you prepare all these. All these are important, and this extra, whatever extra I have just explained to you. This PPT again I will send to you. Okay.